All right, so today we're going deep into computer architecture.
Ooh, exciting.
Yeah, you've given us diagrams, text excerpts. It looks like we're going to really figure out how computer hardware works.
The nuts and bolts.
Yeah, and I think even if somebody is not like a hardcore techie person, they can still get a lot out of this deep dive.
Definitely. I think understanding these fundamental concepts is really valuable even in our increasingly software-driven world.
Okay, so we're starting off with something called the von Neumann architecture, which is like the blueprint for most computers.
Right. It's the classic model.
Yeah, and we have a diagram here, which might look kind of complicated at first glance, but it's actually pretty elegant when you break it down.
Yeah, it's all about how the different parts of a computer interact.
So we can see the core components here, the CPU, the memory, and the input-output, or I/O devices.
And don't forget the buses, those lines connecting everything.
Right, the buses, what are those exactly?
Well, think of them like a highway system for data. They move information back and forth between all the different parts of the computer.
So like a bustling city with data zipping around between the CPU, the memory, and the I/O.
Yeah, that's a great analogy. And speaking of the CPU, that's like the brain of the operation, the central processing unit.
Right, let's zoom in on that.
All right, into the CPU.
So you see it has its own little internal structure here.
Like a city within a city?
Exactly. We've got the ALU, the arithmetic logic unit.
That's the math whiz.
Right, and then the control unit, which directs everything.
The boss.
Haha. Yeah, but then we've got these things called registers.
Mm.
What are those all about?
Ah, registers. Those are like the CPU's personal high-speed scratch pad.
Okay, so super fast memory slots right inside the CPU.
Exactly. They hold the data the CPU needs access to immediately,
Gotcha, and then there's the instruction set.
which is like the language of the computer.
Right, so these sets of commands tell the CPU what to do.
Everything from basic arithmetic to more complex operations.
And different CPUs can have different instruction sets, right?
Yeah, like DKA6, which is common in desktops and laptops, and then ARM, which you see a lot in mobile devices.
Interesting, so it's like different dialects of computer language.
Precisely.
Okay, let's move on to memory. Now, our sources talk about the memory hierarchy.
Ah, yes, it's all about speed and efficiency.
And it sounds a lot like how we organize things in our own lives.
You keep the things you use most often close at hand.
Right, like on your desk or in a drawer you can reach easily.
Exactly. The CPU does the same thing.
So at the very top of this hierarchy, we have the registers.
Like having something right there at your fingertips?
Super fast, but not a lot of space.
Right. Then there's the cache.
Like a nearby shelf for frequently used items,
And then you've got main memory.
which is like a bigger storage room further away.
And finally, the disks. Those are like going to the library archives.
Haha, so it might take a while to retrieve something from there.
Yeah, but you'll find it eventually.
And we have this chart that shows the trade-off between speed and size for all these different types of memory.
Right. The faster it is, the less space it has.
Makes sense.
So programmers use this knowledge to optimize their code. They try to keep the most important data as close to the CPU as possible.
So it's all about minimizing those trips to the library archive.
Exactly. It's called the principle of locality. The idea that things you've used recently or things near what you've used recently are more likely to be needed again soon.
So that's how caching strategies work.
Right on.
But it's not just a single pool of memory, right? Our sources mention different segments within the memory itself,
Yeah, it's organized into different zones, each with a specific purpose.
like different neighborhoods.
Exactly. You've got the text segment holding the program instructions,
Okay.
the data segment for variables,
Mm-hmm.
the heap for dynamically allocated data structures.
And the stack.
Yes. The stack, that's a crucial one for function calls and local variables.
Now that brings us to something I find particularly interesting, stack frames.
Ah, yes. Stack frames, they play a vital role in how programs execute.
So can you explain what happens when a function is called?
Sure. Each time a function is called, a new frame is created and placed on top of the stack.
Like a stack of plates.
Precisely.
You add new plates on top, and when you're done, you take them off from the top as well.
And each frame holds the function's local variables, any parameters it needs, and the return address so the program knows where to go back to when the function finishes.
It's all so organized.
It is. And the stack pointer, a special register, keeps track of the top of the stack.
And efficient stack usage is important, right?
Absolutely. It impacts program performance, and there's another reason why understanding the stack is so crucial security.
Oh, right. The source material mentions something called stack smashing attacks.
Yeah, those are nasty.
So what are they exactly?
Well, it's a type of exploit that takes advantage of a programming error called a buffer overflow.
Okay.
So let's say a program expects a certain amount of data. But an attacker intentionally provides more data than the allocated buffer can hold.
Oh, I see.
This excess data can spill over and overwrite adjacent memory on the stack.
So they're basically smashing the stack by overflowing the buffer.
Exactly, and that can allow them to inject malicious code.
Wow, that's kind of scary.
It is, and it highlights how important it is to write secure code.
So understanding these low-level details can actually help prevent vulnerabilities.
Absolutely.
This is all so fascinating. It's amazing how these fundamental concepts underpin everything we do with computers.
It really is a testament to the ingenuity of computer science.
It's like we've peeked behind the curtain and seen the magic happen.
Uh-huh. Yeah, but we've only scratched the surface.
I know. I can't wait to dive into I/O next.
That's where things get really interesting.
All right, let's take a quick break, and then we'll be back to explore how the CPU talks to the outside world.
Sounds good.
All right, so we've talked about the CPU and memory, like all the inner workings. But a computer is not much use if it can't interact with the outside world.
Right, exactly. That's where I/O comes in.
Input, output.
Yep. All those
Deepen.
connections to the real world.
Like how we interact with the computer.
Keyboards, screens, the whole shebang.
Our sources mention a bunch of different I/O techniques, though.
Oh, yeah, there's a whole variety.
Status-driven, interrupt-driven, program-controlled, DMA.
Sounds a bit overwhelming, right?
It does. What are the main differences?
Well, each one has its own way of managing how the CPU and devices communicate,
Okay.
like different styles of conversation.
Gotcha. So tell me about status-driven I/O.
In status-driven I/O, the CPU is constantly checking in with the device.
Like, are you ready yet? Got that data?
Exactly. It's like constantly refreshing your email inbox, waiting for a message.
Haha. I do that too much.
We all do. But you can imagine if the device is slow, it can be really inefficient.
Yeah, like waiting for a website to load forever.
Now, interrupt-driven I/O is a lot smarter.
How so?
Well, instead of the CPU constantly asking the device, just sends a signal when it's ready.
An interrupt.
Yep, like, hey, I've got something for you.
So the CPU doesn't waste time checking all the time.
Exactly. It can focus on other tasks until it gets that interrupt.
Makes sense. What about program-controlled I/O then?
Ah, that's where the CPU is a bit of a control freak.
Oh!
It directly manages every single step of the data transfer.
So like a micromanaging.
Haha, yeah. It gives the CPU a lot of control, but it can be slow because it's involved in every tiny detail.
I see. And DMA is the opposite then.
In a way, DMA is like giving devices direct access to memory.
They don't need to go through the CPU.
Not for every single transaction. It's much faster that way.
So DMA speeds things up by freeing up the CPU.
Right on. Now let's think about some real-world examples.
Like keyboards and screens.
Exactly. Those typically use interrupt-driven I/O.
So when I press a key, the keyboard sends an interrupt.
Yep, saying, hey, a key was pressed, come handle this.
And the CPU jumps in and processes it.
Right. What about other devices, like network cards?
Do those use interrupts too?
They do. They interrupt when they receive data packets.
And timers.
Timers, too. They trigger interrupts at specific times.
So interrupts are used for anything that happens unpredictably.
Things the CPU can't plan for in advance.
Gotcha. So can you walk me through what happens when the CPU gets an interrupt?
Sure, the CPU has to stop whatever it's doing.
Like drop everything.
Pretty much. It saves its current state and jumps to a special routine.
Well, the interrupt service routine.
You got it, or ISR for short.
What happens in there?
The ISR handles the specific event that triggered the interrupt.
Processes the key press or the network data.
Exactly. And then it hands control back to the main program.
So this whole process of switching back and forth is called a context switch.
Right. It's like you're reading a book.
And the phone rings,
You bookmark your place, answer the phone, and then go back to your book.
picking up right where you left off.
Exactly. That's essentially what the CPU is doing.
Saving its state before handling the interrupt and then restoring it.
And this all needs to happen really quickly and efficiently.
Especially in systems that need to react fast.
Real-time systems, like in a self-driving car.
Right, any delays could be a problem.
It really highlights how crucial I/O and interrupts are
It's like this constant dialogue between the CPU and the outside world.
in enabling all sorts of things, from basic user interactions to complex systems.
We've covered so much ground here,
I know, it's amazing how much goes on behind the scenes.
and we're not done yet. In the last part, we'll zoom out a bit.
And see how all of this connects to emerging technologies.
Okay, sounds good. It's incredible how much we've uncovered about the inner workings of computers.
I know, right? From the tiny transistors to the complex interactions between hardware and software, it's mind-blowing.
We've gone from the CPU's instruction set to memory hierarchies, and interrupt handling. It's like a whole new world.
And it all comes together to create the seamless experience we have when we use our devices.
Exactly. But it's not just about appreciating the complexity. It's about understanding how it all impacts us.
All right, like for software developers.
If they understand these low-level details, they can write better code.
More efficient, more secure.
Like they're playing the game on a whole other level.
Knowing the rules inside and out.
And remember those stack smashing attacks we talked about? Understanding memory management is crucial for preventing those.
Absolutely. It all ties back to these fundamental concepts.
It's like having a secret weapon. You can anticipate problems and build defenses that others might miss.
And it's not just traditional software development either. Think about all these new fields emerging.
Cloud computing, artificial intelligence.
They're pushing the boundaries of both hardware and software.
And as these technologies evolve, understanding computer architecture becomes even more important.
Absolutely. Take cloud computing, for example. It relies on these massive data centers with incredibly complex hardware setups.
And AI algorithms often need specialized hardware to run efficiently.
The lines between hardware and software are blurring more and more.
It's like we're entering a new era of computing, where a deep understanding of both is essential.
It's not just about writing code anymore. It's about understanding how it interacts with the hardware to create the best user experience.
We're really seeing the convergence of these two worlds.
And it makes you appreciate the brilliance of those early computer scientists who laid the groundwork for all this.
They really set the stage for the amazing advancements we have today.
And as technology continues to evolve at this crazy pace, understanding those core principles will be even more crucial.
Absolutely. So as we wrap up this deep dive, what's the one key takeaway you want to leave our listeners with?
I'd say never underestimate the power of understanding the fundamentals. Even as technology becomes more complex, these core concepts of computer architecture will always be relevant.
It's like a solid foundation that you can build upon.
And who knows? Maybe this knowledge will spark some new ideas. Maybe you'll see connections to quantum computing or edge computing.
The possibilities are endless. Well, it's been an amazing journey exploring the world of computer architecture.
I really enjoyed our deep dive.
And I hope our listeners have gained a newfound appreciation for the incredible machines that power our digital lives.
Thanks for joining us.
And until next time, keep exploring.